Okay, the next example is the retirement planning example. Again, we have here is the deterministic model that we set up in the previous chapter. Now we have um, three different input cells or uncertain values, which are annual raise. We assumed annual raise to be 2%, but it could be different from 2%, 0%, or much more than 2%. So again, we have to come up with some reasonable probability distribution for that. Then the annual return, rate of return, we assumed 3% above inflation. Again, that there is no guarantee that would be the case. And then we have retirement living expense that we assumed will be $50,000 per year, but it could be different as well. So these three cells are going to be not deterministic, but to be simulated. Okay, and we're going to assume. Okay, later we will see an example where we have raw data and we can try to fit the most accurate or most um, probability distribution that very closely resembles the data. That we will do that in the future. But right now, let's assume that these are the minimum, most likely, and maximum values. So minimum, most likely, and maximum. Okay. And make sure that they are aligned properly. Okay, so 0, 1%, well, 1%, and 3%. All right, so then we have to use that here. Okay, once again, we've done this before. There are 2-3 different ways in which it can be done, but when you use distribution define and then select the distribution that we want, say PERT, then you get to see what that distribution will look like, and you can visually confirm whether it's reasonable or not. So minimum is that, most likely is that, and maximum is that. Okay, and then we click OK, and then this time we'll leave the risk static as it is. Risk static, it's 2%. So which means that when you run the simulation, as different values are simulated for annual raise, but what you will see in the sheet is the static value is 2%. But actual simulation it'll be different. Okay, annual return, we're going to use normal distribution, so mean and standard deviation, right? Again, let's formulate it, format the cells. So mean is 4.7% and standard deviation is 17.5%. Okay, let's increase the. All right. So then again, we can either type the function risk normal, or you can go to function here and select risk normal, or you can go to distribution, define, and select continuous. It's a continuous distribution, and normal distribution right here. Select distribution, so it gives you the shape. Again, here we're going to change this mean to that cell. Now when you insert a cell address, it makes it easier for you to experiment. You can change this mean and standard deviation without having to get into this distribution and change the value manually. Okay, so that would be the rate of return, and then we have 40,000, 50,000, and 60,000 as possible values or expenses that you expect in your retirement. Okay, annual expense. Now here again, the inserted static value is used for display. So here I'm going to type in risk part, and the three values are from these three cells. Okay, and we can manually enter, if you like, risk static. Well, I pressed enter too soon. You can put any value you want, actually. So risk static. Okay. Let's make the risk static 50,000 as we had before. Now before we run the simulation, we have to set the output. So our objective is to look at how many years the fund will last. So select that and make that into an output cell. So it adds this label as well. So let's edit that, and then we want the name to be just year fund runs out. Okay. Now there is one thing that we need to consider or take into account before we run the simulation. Okay, that is, we assume that the rate of return, annual rate of return, will follow the normal distribution with mean of 4.7 and standard deviation of 17.5. Okay, and that's what we set up here. Okay, and if this is the way we're going to set up the model, then the return for all the years is going to be the same that we simulate here, right? So if it's simulated to be like, if I can do this, okay, so that's like run the simulation one time, so that's 9%. So it's going to assume that it is 9% for all the number of years, 30 to 170 years, will be the same return. So if I click that one more time, so it will be one more run, so 3%, 22%, it's going to be 22% all the way through. But that's not valid, because your return is going to be different each year. So we really should simulate the rate of return individually for each year and then compute the return based on that. So let me insert, okay, cells. All right, so I shift to the right. Okay, so let's say rate of return here. Okay, all right. So now we want to set up this formula. Okay, I'm going to go into edit mode, Control C for copy and put it here. Okay. But now C7 and D7 should be absolute reference, so I can copy it to the rest of the years. Okay. Now that would be the return for the first year. Okay. Then I can do it. So, and then you can multiply instead of $B7, I multiply by this rate of return. Okay. And then I copy these two formulas. Okay. Okay. Now I have rate of return percentage simulated individually for each year. So now I can run the simulation, right? So now let's run it just one time. Okay, so now we have the output, and you see the number of years is on the x-axis. The year fund runs out, and since we are only simulating up to 100 years of age, there is a spike here. But when you look at it, it looks like, suppose if 80 years is you expect to live till 80 years, for example, then there is almost a 50% chance that you'll run out, even though there are some probabilities that it'll last till 100 years, but there is a good chance. Okay, suppose we expect to live till 85, so there is more than 50-50 chance that you will run out. So it will only last up to the funds will run out before that. So it's not looking very good. So let's now try to run what happens when we change the employee contribution. Okay, what happens if you contribute more or less. Okay, so what if analysis based on the decision variable.